All right, so I'm gonna do I'm gonna do that water bubble problem, but I just want to note that it's now on my list of all possible fluid properties problems. For some reason, when creating a PDF, it didn't create a line there, but whatever. Okay, so this is the problem that we want to do. Okay, consider a water drop suspended in air on a pressurized spaceship. G equals 0. The drop is held together by surface tension forcing acting along the outer edge of the drop. The pressure outside the drop is atmospheric, and the drop has a radius of 4 millimeters. Okay. What is the pressure inside the drop? Okay. So I'm going to do this as if I'm going to get out my trusty-dusty ruler here, and I'm going to pretend that I'm working on a sheet of engineering paper instead of on the internets. Okay, so what we'll do here is we'll label this. This is homework 2. I think I might have called it homework 1 on the sheet, on the key, but that's fine. This is the class, and then my name, R. Wayne Wagner. Wagner. And this is page 1 out of, well, maybe it'll be 1. It's actually probably going to be 2, but I guess we'll see. Okay, so, I'm going to use white here. Okay, so we would write our givens. Okay, so the first thing we're given is we've got a droplet. Okay, I'm not very good at doing circles, but I am on a computer, so I should probably take advantage of that. So let's see if we can do that. Let's get a circle, okay? There's probably some kind of way to make this absolutely a circle and not an oval, but anyway, so we've got a droplet. And on that droplet, we'll say that this is a droplet. Okay, what else are we given? Well, we know there's no gravity. Okay, I gave you that there was no gravity because I didn't want you to worry about, hydrostatics. Oh, this is water, so that's an important thing. And then we were told that the droplet is held together by surface tension. Surface tension. What else do we know? I think that's pretty much it. Okay, there's not really a lot given. So then what do we want to know? Okay, required. Okay, so it says if the pressure out equals the pressure atmospheric, which of course is like weird, right? Because we're in outer space. So is there really any atmospheric pressure? But it doesn't matter. We're going to use 0 gauge. So it's going to be relative to whatever the outside atmospheric is. Okay, and the radius of this bubble is 4 millimeters. Okay, then what's the pressure inside? Okay, and then the last thing, so this is part A, and then part B, because, sometimes, I want you to think about how these things work. So we said as the radius increases, the radius of the droplet increases, okay, what does the pressure inside do? Okay, so we're looking for a relationship there. Okay, so I'm going to zoom in over here, and we're going to solve this twice. And that's why I'm anticipating 2 pages here. I'm not sure if I like the white on black. I think I prefer the black on white, but whatever. Okay, so here's the solution. So there's 2 solutions. I'm going to start with the easier of the 2 solutions because it doesn't involve calculus. And so what we're going to do here is I'm going to do a free body diagram of a cylinder. So this is kind of like the clever solution that bisects the droplet. Okay, so what that means is basically I'm going to draw a line through the middle of this droplet like that, and I'm going to have a cylinder up there. Okay, so the whole top of that cylinder is air. So here's my cylinder. Let's see, how can I do this? It's not easy to figure out how to do this exactly properly, right? So here it is. So here we go. Okay, so it's a cylinder, so the bottom of it looks like that. And, probably I could use that fancy schmancy tool. Okay. Now, the interesting thing about this, of course, is at the bottom of it, it is kind of comprised. It is the water droplet, right? So the water droplet is the bottom of this thing is the water droplet. Okay. So what's cool about that, or what's important about that is So if I'm going to zoom in on that water droplet, and this is also one of the nice things about a computer here, is that I've got this this surface tension, and it acts only on the surface, and it only pulls. Okay, so it acts along this backside too. Okay, so that force is, so that's the force of surface tension. So that should be a subscript, excuse my horrible language, drawing here. Okay, and that is found as sigma times the length over which it's acting. So the length in this case is the circumference of that circle. Okay, that's a downward force. Okay, in the meantime, we've got two pressures, and I'm going to do the pressures in, I don't know, green maybe? Okay, because the problem is these arrows tend to cross over each other, right? But the pressures are acting on this whole circular face, right? So they're acting all in here, okay? So they are going up, okay? And right now I'm drawing them on the edges, okay? But the edges aren't really important. It's actually mostly what's happening on the area, right? A pressure is a distributed force distributed over an area, okay? So the surface tension is a force distributed over a length, but this is the pressure. Now it's the pressure inside the bubble, okay, times that area, and that's going upwards. Okay, so I could call that the interior force or whatever I want to do. Okay, so now we'll zoom out and we'll get the top of this thing. Okay, and the top up here, I don't know if I have maybe we'll do blue up here. Okay, so same idea, but I've got the pressure here, but this pressure is just in the air, right? So this is the outer pressure, okay, and it's distributed over this whole face. Okay, normally you wouldn't spend your time drawing all these arrows, right? But anyway, so this is the outside pressure distributed over that area, okay? So we've only got three forces on this thing. Now you might say, well, what about the forces, around the outside of this thing? There are forces out here, right? There are pressure forces, I can't draw them in 3D, but they're all acting on the outside of that cylinder, which we should take into account. But the reason we don't take them into account is because they all cancel. So we're not going to worry about those, okay? So what we're going to do is we're going to say, okay, well, the sum of the forces in the y directions equals 0. Okay, so the first force is we've got the positive force of the P in times the area. Okay, we're going to subtract the P out times the area. And then we're going to subtract the surface tension force, which is sigma times the length. And we'll say all that equals 0. Okay. So the only thing here, and this is like kind of the trick to this problem, is remembering, remembering the area of the circle. Okay, so Pn times the area, pi r squared, minus P out times the area, pi r squared, minus the sigma times the length, which it's acting again on the circumference of the circle, 2 pi r, equals 0. Okay, so what's nice here as we work through this algebra, the pi's are going to go away. This r is going to go away. Those squareds are going to go away. Right, and I can rearrange this. And the way that I prefer to think about this is P in minus P out equals 2 sigma over r. Okay, that's the way that I prefer to think about it, but there are other ways. For this particular problem, this one is a gauge pressure, so that one's going to go away. So we're left with P in equals 2 sigma over r. Okay, and so from right there, we should be able to see that as we add larger and larger numbers to r, so this is part B, that Pn is going to get smaller. So right here, I could just kind of do an aside and say, okay, as r increases, okay, P in decreases. Okay, so that's part B. Okay, for part A, we need to just plug some numbers in. So say, okay, well, P in equals 2 sigma. Now you have to look up the sigma off the interwebs, or really your textbook has this. But this is a pretty standard value, okay? And then we'll divide by r. R is, 4 times 10 to the minus third meters. Okay, and then so we'll say, okay, well, Pn equals, if you do the math there, you're going to get 36.5 newtons per meter squared. Okay, so newtons per meter squared, or if you prefer, and I often do, 36.5 pascals. Okay, so those are your answers. Okay, noting that we've got a newtons on top and we've got 2 meters on the bottom. Okay, so that's how we do this the quote-unquote easy way. So this is part A. Okay, very colorful, very beautiful, a lot to like. Okay, I'm going to do it again. So I'm going to go ahead and declare that I'm going to have a second page. So we're going to go over here and I'm going to do this again, but I'm going to do this quote the hard way, meaning I'm going to use calculus. So if ever this is, so if you just wanted the answer, maybe that was all you needed. So homework 2, spring 2022. Okay, this is ENCE 3318. That's my name. Don't wear it out. And of course, 2 out of 2. Okay, so now everything here is the same, except I'm going to do a different free body diagram. Okay, so free body diagram of the top half of the bubble, of the droplet, droplet. Okay, this is harder. And let's see, I can't draw a half bubble. Okay, so I'm just going to, not with the tool, so I'm just going to do the best I can here. Okay, ooh, that came out pretty good. Let's see about the other half. It's not terrible. All right, so then we've got this bottom bit right there, and then we've got, this thing there. Okay, so free body diagram of the top half. Okay, the bottom of this thing looks just like what we just did. So I'm going to scroll out over here. So the bottom half of this thing is exactly like this. Okay, so there's no reason, I'm not going to double that up. I'm just going to draw it as a single area, P and A, and F equals sigma L. Okay, so we go over here. Where is it? Okay, so we've got, I'm trying to remember the, the colors that I used, but we've got a downward force, maybe I'll put it right here, of F sigma equals sigma times L. That is the worst sigma I've ever done, so we're going to erase that. Okay, and then we've got an upward force, which I'll show acting on that face, of Pn over that area. Okay, the hard thing here is what about this top force, where it's the outside pressure? Okay, now we could just step back and say, well, the outside pressure is 0 because this is, because the outside pressure is 0 in this case because it's atmospheric, et cetera, et cetera. But I don't want to do that, okay? Because I want to show you how to do it if you were working for, and you wanted to do it this way, okay? So what we do in this case, this is the algebraic way to get at this, is I'm going to think about a single ring of this bubble. Because, so the problem here is this. If I look at like this individual thing right here, some portion of it is going left-right, which I don't care about, because what I'm going to do is I'm going to say the sum of the forces into y equals 0. So I don't care about the left-right bits of it. I only care about the vertical bits of it. So this one right here, I don't care about at all for the most part, because it's going straight to the left. This one, right up here, I care about almost all of it, because it's going straight down. So the question is, how do we deal with that? Okay. So, so what I want to do is I want to consider, these two, so if I just draw a vertical line, a horizontal line from here to there. Okay, I want to consider this ring. Okay, and what I want to do is I want to consider the pressure force on that ring. Okay, and so the pressure on the outside, well, that's P out. Okay, and it's acting on this little differential area. Okay, so so the total force of this whole pressure on that thing is the pressure out times the area over which it's acting. Okay, so don't let that D confuse you. It just means it's a small little area. Okay, and so it's kind of like, well, how do we figure out what that area is? Okay, and to do that, we need to think about what this thing looks like. So if I were to take that strip right there, okay, now it's wrapping around this thing. So if I were to take that strip and if I wanted to look at it from above, right, it's going to look like this. Okay, again, a bad circle, a horrible circle, in fact. But I want to look at this strip, right? So from above, it looks like this. Okay. And what I could do is I could snip it even. I could snip it right here, and I could bring it down here, and I could say, well, then what would it look like? Well, if I unraveled it, it would look like this. All right? Okay, so I just kind of cut it here, and I unraveled it. All right, so then what I would need to do to figure out the area of this thing is I would need to figure out, because that's what I'm trying to figure out, right? I've got this pressure out, which is easy because it's just P out, but then I need this area. What is the area of that thing? Okay, so I need to know this thickness right here of it. Okay, so I go back over here. That's this thickness right here. Okay, well, what is that over here? Well, that's the distance from here to there. Okay, so let's see. So how do we get at that? Okay, so we're going to start right here. And what I'm going to do is I'm going to try to figure out, this thing right here. Okay. Now, usually what happens in this case is, or really in any case, is I know that this distance right here is r, right? The radius of this circle goes from here to here is r. So the radius from here to here is r. Okay, the arc length is defined. So this is the arc length right here. That's the arc length. Okay, and it is defined as r times the angle right here that we're looking at. Okay? Now, because ultimately I'm thinking of this as a calculus way, what I'm going to do is I'm going to add up all these little arc lengths one at a time. I'm going to add up, I'm going to add up all of these, strips. But the way I'm going to do it is I'm going to do them a little angle at a time. So if this angle right here is phi, then this little tiny angle right there, that's going to be my d phi. Okay, d phi. All right. So there we go. Okay, and that's how we get this particular thing right here is r d phi. Okay, it's just anytime you have an arc, you take the radius and you multiply times the angle. Okay, now the key here, of course, is the angle has to be in radians. Okay, that's how this whole thing works. Okay, that's why radians are a really wonderful thing to work in. All right, now what about this distance right here? Okay, how do we get that? Well, I guess I should be consistent. I should be in blue. Okay, but how do we get that? Well, that's the circumference of this circle right here. Okay, so that is the circumference of this circle right here. Okay, so what I need to know more than anything else to get any kind of circumference is I need to know the radius of that circle. Okay, so I need to know the distance from the center of it, okay, out to the edge. Okay. Well, the nice thing about this is we know trig, right? So if you know trig, then this is, trivial, right? Because here we go. We're going to just draw a little triangle here. Okay, we're going to go straight down to here. Okay, and we're going to go this way. And here is the thing we're looking for in red, right? We're looking for this right here. R is in white. We want this thing in red. Okay, well, if the hypotenuse is r, we've got an angle theta. This is going to be r cosine, not theta, phi, r cosine phi. That's the radius. Okay, so the circumference of any circle is 2 pi times the radius. Okay, so over here, this is 2 pi times the radius, which in this case is, r cosine phi. Okay? So the area of this thing, which again, it's just a little differential area, okay, is going to be this thing times this thing. Okay, so it's going to be 2 pi r squared cosine phi, and then a little d phi. Okay? This is, it's not Halloween, but this is very scary. Okay? But don't be too scared, right? It looks very ugly, okay? But, nothing too terribly complicated has happened here, okay? So, if I want to know the force on this little tube right here, okay, then the force on that little tube, okay, so what would I want to call that? A little dF maybe? Let's call that dF, d force of pressure, equals, well, let's not go off on an angle here. That's going to get weird. Okay, so based on everything that I just did, I'm going to say, okay, well, the F pressure. Okay, so that's just a pressure on this one little, whatever we want to call that, cylinder or line around Charlie Brown's head or whatever. Okay, equals the pressure on the outside times the differential area. Okay, so I'm plugging and chugging right now. And this thing is going to get in the way, so we're going to get rid of it. Okay, equals P out. Come on, baby. It always freezes as we get into this thing. P out, okay, times that area, which I decided was 2 pi r cosine phi, r squared cosine phi, okay, d phi. All right, now, and here's the last bit right here. Right, it's tempting at this point to come in here and integrate that, okay? But integrating that is not helpful because you really can't integrate that because all these pressures are not in the same direction. Okay, so essentially in that case, we'd be adding up a bunch of things that go in different directions. So we'd be kind of breaking rules of vectors. So what we're going to do instead is I'm going to try to get the y component of this. Okay, so what I'm going to do is I'm going to say d, come on, give me that, d, f, p in the y direction. Okay, so this was kind of like a vector here. And we're gonna basically scalarize it, or I don't even know if that's a word. But what we're gonna do is we're gonna say, okay, well, this is right here, so this angle right here, that's phi, okay, from similar triangles, right? But we only care about the vertical component of this thing, because all the horizontal ones are gonna cancel because there's another one on the other side, right? So this thing needs to be multiplied by, or this thing needs to be multiplied by the sine of phi. Okay, so it's gonna be P out, 2 pi r squared cosine phi times the sine of phi, okay, d phi. Okay, so it's almost on the way to d phi q. Sorry. Anyway, so here's what we've got to solve for that. So if I integrate this, so fp in the y, so that's due to the, no, not fp out, but it could be fp out. Fp in the y direction equals, okay, you know what I'm going to do? I'm going to rearrange these because of the way I think of my chain rules here. So I'm going to make this cosine, I'm going to make that, or sine that cosine. Okay, so sine of phi, come on, baby. Okay, here we go. Sine of phi, cosine of phi. All right, so here we go. P out. Okay, we're going to integrate 2 pi r squared sine of phi cosine of phi d phi. Okay, noting that sine and cosine are kind of the chain rules of each other, or they're the integrals of each, they're the derivatives and integrals of each other. So taking this derivative is actually not all that difficult because, so equals, so let's see, we're going to pull out the p out, we're going to pull out the 2 pi, we're going to pull out the r is a constant. So we're going to end up with 2 pi r squared integral of that sine phi cosine phi d phi. Okay, and we're going to go from 0 to 90 degrees because that will cover the entire circle, because we're going from, phi is 0 until phi is all the way up here, at which point we will have covered the whole thing. Okay, and now I've got this sine cosine. So remembering that the derivative of a sine is cosine, this is going to become sine squared of phi 1/2. Oh, well, looks like I integrated it already. Sorry. So, all right, so let's, I just went straight into it and integrated. So here we go, like that, okay? And so I guess we could put the pi over 2 and the 0 up here, but pi over 2 and 0 down here. Okay? So that's kind of a cool result because, like, if you do this, the 2's can't, like, if you were to integrate or take the derivative here, right, the 2's would cancel, you get sine of phi, and then you do the chain rule and you get the cosine of phi. Okay? So anyway, so fpy equals, we're going to note that this 1/2 and this 2 are going to cancel, so pi r squared times the sine squared of phi. So if I plug in 0 for the sine squared of phi, that's going to give me a 1, which we square, and we're going to get 1. And then if I plug in the 0, the sine of 0 is 0. So it looks like that, right? Oh, wait, where'd my P out go? Oh, here's my P out. Okay, so times P out. Okay, so in this case, FPY equals, P out times pi r squared. Pi r squared. Okay? So, that's pretty much it. Okay? So that's the vertical force in the y direction. Somewhere in here I didn't account for the fact that it was downwards. So I guess technically, this was always downwards from the very beginning. So I could have put a negative sign all the way through here, right, if I'd wanted to. And that would be true. Okay? So let's go over here. And here's my free body diagram. And I'm going to replace all those blue pressure lines with maybe a bright yellow P out times the area, right? Pi r squared. Okay? So what you do at that point is you take this force, and this force, and you just do sum of forces in the vertical, okay? And so you just plug them in just like we did a second ago down here, and you come and get the exact same answer, okay? So that is a solution, okay? I don't recommend that one for, brevity, but I like it, it's fun. So, difficult if you're not comfortable with calculus, okay? But that's the idea. Okay, so I hope that's helpful, and as always, take care of yourselves. Remember, you are way more important than any of this stuff, okay? So take care of yourself, and I will, guess I'm seeing you guys tomorrow, so I'll see you tomorrow. All right, bye.